for an ensemble method, again, is so-called gradient boosting. We've already talked about boosting today and before. Remember, this is when we are sequentially building one model after another in order to take the issues that the earlier models had and specifically laser focus on those to predict and improve on these. And in the case of classification, that means we want to improve our classification error. This is something we've already gone through in quite some detail, so I'll be quick right here. We already know this slide, some history of where it got. But now the difference with gradient boosting is this is a sort of a generalization on this approach, which gives us some additional power. What we want to do here is we are making it possible to use an arbitrary loss function, not just in the case of a regression model, let's say, the mean square error, but for other problems, other loss functions might be more appropriate, and this is what enables us to do so. So it's basically an extension which uses some mathematical trickery and derivation to make this possible. What we are doing is we are calculating the gradient of our error, of our loss, which is basically the direction where we need to tweak the model in order to improve our performance. So since we can then formulate this in the shape of a derivative, say we are putting our target function into this shape here, which is basically the sum of all our losses across all of our samples, given some initial model f on all the samples. We're then building a derivative of this loss function given our model. And this is the gradient, and it's probably easier to think of it in a more visual way. This is very closely related to the gradient descent algorithm that is used for some other models, such as neural networks, where we are thinking of all the different model weights, or in this case, all of the different trees that we could have as a sort of landscape. And ideally, we would want to reach those models with the lowest possible error, i.e. the best possible performance. And we can do that by slightly tweaking the model in one way or the other. And the direction where we want to go, that's called the gradient. And this is very, very similar to boosting, where we also remember we figured out the residual of our error function, and we built a model to predict the error. However, by doing it in a more general way with the gradient, this gives us just some additional mathematical power and options. So we can use other loss functions, and at the end of the day, what we are doing right here is very similar to what we did with the boosting step. So we're calculating an initial model. We're figuring out the residuals, what was the problem of the true value in the sample minus our original model. And that's our new model prediction. And since we're using this gradient, which is not exactly the same, we also need an additional size parameter, rho in this case. for gradient boosting, this was not necessary. It's basically always one. We just use the additional model directly. But in this case, this is also a parameter that gets optimized by our model. Given the new tree, it's also finding this step size to ultimately get the best possible performance for whatever metric we imposed on the model. At the end of the day, we still need to make all of the similar choices for the hyperparameters as for regular decision trees. But one very common thing to do is, since this gradient boosting gives us such a powerful way to build an ensemble of methods, of weak models, the individual models in the chain, they can be really, really weak. So, for example, it would be possible to just use a single split in the tree, only 2 leaves at every iteration of the sequence of the boosting algorithm. However, since we're so laser focused on the specific situations where the model is still having problem, it's very easy for this process to run into issues with overfitting. Because if there's a problem anywhere, it's trying to get rid of it. And so it's easy, if we are letting it run for too long, to pick up some relationships that are not generalizable, that are just overfitting. And this is actually one of those situations where the gradient boosting generalization gives us some additional power, because we can introduce a learning rate parameter. We are basically, when we're doing a gradient descent, we are kind of at risk of overshooting. So let's say if we're thinking again about the shape of the theoretical landscape of all possible models and the performance that these models have. And we are then using gradient descent or gradient boosting to go, hold up, let me change color right here, to go one step, and hopefully we are getting closer and closer to the middle right here. However, if our steps are too large, then we might overshoot and end up not in the middle, but rather somewhere outside. And in order to avoid that, we want these steps to be sufficiently small that we do not end up in this unstable situation, but still large enough so that we are reaching this local optimum right here in a reasonable amount of time. So that's what the learning rate is for. And it's yet again one of those hyperparameters that we need to set to some amount. And it's difficult to say in advance what would be.
Sebastian, can I make a quick question?
Yes, of course.
Can you prove that there's a global minimum? I mean, could it happen that you fall within a local minimum, and maybe if you moved your procedure somewhere else, you could actually achieve even a better solution?
We are always, unfortunately, with these gradient descent or gradient boosting approaches, aiming for a close local optimum. So in general, I'm just going to use the space I have right here to get everything. In general, this algorithm is just going to hunt the local optimum. So if we are starting at some random point right here, then gradient boosting and gradient descent will push us into the local optimum. But there's no way to prove that this is the global optimum. So this is another case where, for example, cross-validation is giving us some advantage, because when we are forced to use some sort of random initial point, or the initial point very much depends on those initial samples that we have, then our starting points might end up on different points in the landscape. And so they will end up in different parts of the valley, or of the overall landscape. And hopefully this way we can get some measure of what the once again confidence range of our model is. Does it always perform really well? Does it always end up with a sort of similar performance level? But in general, yeah, this issue of using gradient descent only giving us only local optima is something we need to keep in mind. That's a very good point.
Yes, very, very, very good question. And I think if we make a parallel to, for example, another setting in which we also have this issue. So, for example, with neural networks, there we have a starting set of weights. So what we would typically do is to randomize this starting set, to say I'm going to start with several different sets and see, does that make a big difference into my final result? Now here, we don't have that that starting set of weights. So as Sebastian mentioned, we would then typically use the observations as a way of including some randomness in my starting point, if you will. And even though this is not really part of the original idea of gradient boosting, what most packages will also allow you to do afterwards is to also limit the subset of variables that the trees can see in each split. So in a similar fashion as random forest, in a sense, combining both ideas of having this randomness. So this is also something that could change your starting set in a sense. But in a nutshell, it's a trial and error to try to see if you land in the same region or not.
There are some advanced methods to try to avoid this problem of getting stuck in a local minimum. For example, including some sort of momentum, so that if we're moving this metaphorical ball in one direction, then it keeps some of its speed to get over those little bumps in the landscape. But that's a bit out of scope for this class. But there are further techniques to avoid these issues of getting stuck on a local minimum. Now, you might have noticed that both this learning rate and the total number of trees are in the ensemble are really closely related together. So, or they're having a similar effect on the overall model at the end. Since every additional model in the chain is slightly improving on the performance of the previous one, we can reach the theoretical optimum more quickly by having a higher learning rate, because if we are fully exploiting the new model to optimize our arbitrary loss function, then we would get there really quickly. Alternatively, we could take small and careful steps, but then we might need more models in the tree, that each of them have a smaller weight, a smaller input. But at the end of the day, we are hopefully then reaching the theoretical optimum in a more stable way. So if we want to reach the optimum point, we in the best in the shortest amount of time, we need to kind of trade off between these two parameters. And as we just mentioned, we ideally want some sort of randomness in the initial conditions of the model and of the trees, so that we have some shot at exploring the entire landscape and not getting stuck in a particular local minimum. And that's one of the things that stochastic gradient boosting is trying to achieve. Basically, it's training each model with a different selection of the training data, similar to the bagging model. And this way, it's achieving some sort of randomness, which gives it at least some probability of reaching a global optimum. Some of the other parameters that we once again need to choose, it's getting quite a lot of parameters by now. So we have now the option to choose an arbitrary loss function. We're no longer limited to what we had before, like the mean square error in the case of a regression model. We already had the number of trees before in the random forest model. We now also have the learning rate, tree depth, and minimum number of observations in each leaf node. We already had those before. The fraction of observations that are getting randomly selected, that's new. So it's getting more and more parameters. There's no free lunch, as we like to say. If we are having these more complicated models, we have the chance of better performance because of all these intended benefits. But in order to reach that, we need to somehow pick good values for these. And that's really a mixture of experience, best practice recommendations, and trial and error for whatever your given data set is. So we are doing that for the lone default data set that we are now so familiar with, and the performance that we got on for the settings that we'll be looking at in a moment on the full data set are actually looking really, really good. This is finally a model that is achieving even better performance than the conditional inference trees, the original decision tree model. And since this gradient boost algorithm is also something where a lot of research and a lot of engineering has went into, there are some really good and well optimized libraries available to us that are able to calculate the gradient really, really quickly, and therefore able to optimize this in a really, really quick way. Because generally speaking, this is more computationally expensive. When I say in a quick way, I mean, considering the difficulty of what we're trying to achieve here, it's going to be slower than some of these earlier methods, definitely.
And perhaps just one additional piece of information there. So we're going to have in our code 2 implementations of gradient boosting, and one is the traditional, if you will, GBM package, and the other one is another implementation called XGBoost. So there's a slightly modified version of the original algorithm that actually gets very good results and is much, much faster than the original implementation of gradient boosting. And that's actually the one we see here. So that's this gradient boosting on steroids, if you will. And we can get into more details later on. What are the major differences between the original gradient boosting and XGBoost? But you might see, if you're curious about it, look at these data mining and data science competitions. And more often than not, XGBoost or ensembles that have XGBoost results within them typically do quite well. So for many years, they were invincible on the top of those competitions, and still nowadays they get very, very good results.
And XGBoost, that is one of those libraries that I mentioned that is independent of the actual programming language that you're using. So doesn't matter if you're using Python or R or Julia, that's a library that you can use from any of these languages. So we'll be taking a look at that, how to do that in a moment. But once again, in a bird's eye view of gradient boosting, we're still limited, or we're still forced to consider these trees and their performance sequentially. So parallelization is not possible, and that makes it much slower than simple bagging models. However, it's able to exploit much more the landscape and fine-tune the final bit of the loss through using the more the later models in the later trees in the sequence. And by using stochastic gradient descent, stochastic gradient boosting, we can make sure that hopefully we can reach any possible local minimum. And the main point of this was it gives us the possibility to use any loss function that we can define. So loss functions we can define for a lot of different problems. So this makes this technique actually applicable for a very large amount of, for a very large class of different machine learning models. We'll look at some of the things that we might want to do later tomorrow during the applications and the outlook. But there are more things that we might want to do other than just classification or regression in the narrow sense. But there are, of course, trade-offs. It's we have more hyperparameters to tune. It's taking longer to compute it. That's why there's so much time spent on optimization, and we're happy that we can use XGBoost. But this also makes it difficult to interpret the model again. If we're once again thinking about decision trees, they sound easy to interpret, but that sort of benefit definitely got lost a long time ago. And trying to look into gradient boosted model to try to understand what is going on, it's not very intuitive at all. We'll see that in a little bit more detail when we're looking at the code, which unless there are any new questions at this point, is what we would like to do next.
So there's one question now here in the chat. I think that was directly to me. So he's asking, could you give more details about tools for interpretability? Yeah, so we did mention yesterday, right? So that some of these tools are already built in some of those packages that we're going to use, and GBM is actually one of them. So in the original paper about gradient boosting, Friedman also includes one idea about how do we get to an estimate of the direction of the effects, not of the X on the Y, but of the X on the Y hat, meaning how do my predictions get affected if I change the value of one of the variables that seems to be very important in the model. Because what the variable importance tells us is not what is the direction of the effect. It just tells us was this variable very relevant in my splits, right? So did it influence my predictions by a great deal? But it does not tell us in which direction. Is it that increasing the value of this X makes my predictions higher or lower? Or in our case, because we have a binary variables, does it increase the propensity or the probability that this observation is going to be default yes or no? We don't know a priori, right? So what Friedman introduces in his gradient boosting paper is the idea of partial dependence plots. And the idea is to say, let me keep all the other variables that I have at their mean values, and I'm going to vary just this variable of interest. So let's say if this variable of interest is, I don't know, payment amount. So I'm going to go from 0 to a certain high value. And then I go and see what happens with my predictions at each of those values, right? So I'm making a grid and making as many predictions as values of the X variable that I set on this grid. And that gives me in the end then a curve that I can use to say, okay, so how does this, for example, affect the predicted probability of default yes? Now, there's a caveat with that, actually many, but a couple of them. So one is maybe we're putting values in this grid that are not really observed in reality. So we need to be very careful to interpret the results that we get in this region where we really do not have a lot of density in our data, and especially in reality as well. But if we don't have any, let's say any payment amount of 5,000 in our data, then the model is just assuming something, but it never really observed what happens, for example, when I jump from 4,000 to 5,000. Maybe something totally different happens there. We just don't know. And because of that, the model is just assuming, right? So that's the one thing. So we have to be careful, just interpret these regions where we actually have enough density of the data. The second thing is, because I'm abstracting all the other variables by setting them on the mean, that means that if I have any kind of interaction effects there or any kind of heterogeneity in groups that are a lot more complex, then I would not be able to pick on that. There's another method that you could use for that, which is called ICE plots. So these are individual condition expectation plots. And what do they do there is they do not put the other variables at their means. Instead, they compute as many predictions as you have of combinations of all the values of the other variables that you have in the data set and the values of the variable that you want to look at the graph. So this is computationally very expensive, as you might imagine, but that kind of tries to handle this problem. But again, for some of these tools are available plug and play from the packages of the methods that you're using themselves. Others, you need to use another package but then you can already call them on the object where you save your object. So where you save your model, sorry. So that's the case of ICE, PDP. There's some fancier versions in other packages as well. So you could use those. And I see Raul also asked a question here in the Q&A. So could you please elaborate a little more about how gradient boosting reduces bias while stochastic gradient boosting reduces variance? Okay, so actually both of them attempt to reduce bias, because what you're doing is you're trying to get better predictions by getting each subsequent model to improve on what the previous model did. Right, so we're making this model slightly more complex by trying to improve on what are the predictions that I got from the previous models that I have in this sequence, if you will. So you're always, in both cases, you're trying to reduce your bias there. And what you actually get from the stochastic gradient boosting is that you also will reduce variance by reducing the chance that you're overfitting your original training data. Right, so you include additional randomness there in those rows, so that you make sure that every tree gets the chance of seeing some of those samples, but not all the samples that you originally have. And by doing that, you reduce the possibility of overfitting, as we had also in the past when we said, okay, let's do bagging and let's just use a fraction of the original data set there. But both of them are reducing bias.
Basically, we can think about bias when our model is not powerful enough or flawed in some other way, so that it cannot hit the true distribution on average. And boosting is a way to increase the power of a weak model by generating more and more fine-tuning and laser focusing on the small errors. We can keep doing this until even the tiniest difference from the true mean is finally eliminated. And variance we can think about when we're using the same procedure on some random sample of the data, and the resulting models look completely different. They throw completely different predictions. For example, during this, when we showed this one slide with the random simulation and vastly stupid arbitrary predictions in between those, that's because the model was too powerful it hit those individual values precisely, and the stochastic gradient descent is a way to ensure that it cannot do that, because it cannot see all of the data, and the data that it sees is sufficiently randomly selected that it cannot exploit it to such a degree that this would happen. So all of the resulting models, after we're doing this selection and stochastic approach, their overall results will be similar or less different. The variance is reduced in a sense. There's another question in the chat. Confounding adjustment in the causal forest could be implemented, or co-founding adjustment. I'm not sure, Gabriela, do you know what's meant?
Well, actually, as long as you can, you have this variable available, right? Because that's actually what we're trying to aim at. So when you say, okay, so I have my treatment effect, but I have other things that I have to control for if I really want to get at this effect. And that's our typical conundrum, because we by definition, unless we have simulated data, we don't really know everything that is playing a role there, right? So what are the other variables that we need to control for in our regression? And so let's think about the regression setting, right? And also, what are perhaps additional variables that will give me subsamples or subgroups of the data, and maybe the effect in these subgroups is different, right? So we have, in a true sense, these heterogeneous treatment effects. So the real problem that we have in practical applications is that we do not know all the things that could play a role. But imagine that you would be in a very happy situation that you have all the variables that you would need in your hands, and you're not either forgetting something, or you also you have everything that actually plays a role there. Because sometimes you think of things, but you don't have these variables available to you, right? But imagine we are in this very happy situation. If you would put all of this through the tree, then you should get asymptotically speaking, also good results, because what the tree is doing is actually trying to find this heterogeneity there, and making sure that you do not have estimates that are being shifted in the wrong way because you did not consider this heterogeneity across the group. So meaning you did not consider the interaction of the treatment effect through the different structures, so through the different subgroups that you have there. So assuming that one, you have you have a way of controlling for these confounders, and two, that you let the tree see all of these variables in there, then this should get you asymptotically to good results. And that's something, actually, there's a paper, I can look it up and send it here in the chat. There is a paper from Susan Athey and co-authors that proves this mathematically. I'm going to try to look it up here and put it in the chat.
Yeah, basically, Susan Athey is the real master of the causal forests. Most of these papers she worked on and contributed mainly. All right, if there aren't any more questions at the moment, let's go to the RStudio. Gabriela, do you want to, or should I open RStudio?
I'm looking up the paper right now. If you want to start sharing, that would be great.
Sure. Then let's go back to RStudio, and maybe make the code a little bit larger so they can see it better. And as usual, I've already loaded all of the data sets from the previous days, and still got the results from the previous model in memory, just so that we got it available right here. One of the things we did earlier for the decision trees was to generate some missing values, just to demonstrate the surrogate splits. random forests, at least in this package implementation right here, they do not like that. This package is not able to deal with these surrogate splits, so we need a full data set. We made a copy back then, so Lone's train data small doesn't have any missing values, but if it did, this is one way to impute the missing values back into existence. Now we still want to run a parallel process, a random forest. That's not one of those boosting approaches, so we can use this. We can exploit parallelization. And this is the package that we are going to use. Once again, we exclude this default num categorical variable, which gives away the answer. The random forest is choosing the observations randomly. We can tell him whether or not they can choose the same sample multiple times. And as usual, we need to specify the number of trees and the sizes of the trees and the minimum size of the trees. And the new parameter, that's the this m try factor, that's kind of really the number of, well, as it says right here, of features or explanatory variables that are considered at every possible tree. So the smaller this one is, the more different the trees will be forced to be. And if it is as large as the total number of columns in our data set, then it will not make any difference. And here we go. We've got the results. Let's take a look at this random forest, what it looks like. Unlike the generalized tree before, it doesn't give us all of the nodes and weights right here, because that would just be too many useless numbers. It's not possible for us to get any understanding from that. Instead, it gives us, as before, the confusion matrix. That's something a little bit more useful. And we can also create a plot of this tree. And what we can see right here in this random forest, how it is doing as more trees are getting added to the forest. And initially, it's making some choice that didn't help so much. But as we let it go on for a longer period of time, the error goes down. And I think this dotted red line, that's the ensemble error, or I'm not quite sure at this moment.
Sorry, Sebastian, I was just
what was the difference between the green and the red line in this plot? Is this just the confidence interval?
No, one is the out of bag error, and the other is the error on the training data.
And this is the overall, right?
Yeah.
So the in sample, the error on the data the model is seeing, that's going to 0. Basically, if we are letting the forest grow long enough, it will be able to exploit this number down to 0. However, the fact that the out of sample errors so much bigger, well, that just means that some of those things it learned didn't generalize so well. And here we can see all of the different samples of the data set that we have available. And now here we've got not exactly the percentage prediction, but basically the lower down here, the more sure the model is that it is in one class, and the higher it is that it is in the other class. And the color represents, in this case, the true default or non-default status of a certain data set. So ideally, we would want all of one corner to be blue and all of the other corner to be red. And here, so this way we can see some another visualization of in this area, the model is not so sure, and it's also making some of the errors. But for some of the samples, the model is really, really sure, like 100% sure, but it's still making errors. So yeah, this is just another way to try to get an insight into the model. Another way that we would want is the variable importance plot. Let me just make this thing a little bit bigger so that we can have a better look at it. And that's one of the advantages of this package. It's giving us the option to keep track of the variable importance across the forest. And total payment amount, unsurprisingly, the variable that was the very first split for all of the trees that we looked at before is also one of the variables that is receiving the highest importance. And there are two different measures that are used right here. One is based on, once again, the Gini coefficient, and the other one on the accuracy metric. So it's tempting to interpret this as some sort of significance or causality, but that's really not something that you can draw from this plot right here, because once again, it might be that, well, previously we had the issue that very closely linear variables, the trees are choosing just one of them arbitrarily. But in the random forests, some of the trees are not able to pick some of the collinear variables. So since there are trees that are forced to use just one of them, it is able to get some insight into the relative importance of both of the closely correlated parameters. And unless they have some other thing going for them, they would probably end up with a similar variable importance in these plots here as well.
Yes, it's very, very, very important also to see whether these lead to substantially different results, right? Because often what you would like to do is to focus on the graph on the left-hand side, right? Because that's the one that you generated from these permutation tests. So whenever you have a situation where a variable was preferred in a split because it either had many missings or it had many different values there, then you would see this bias also reflected in the mean decrease in the Gini index. So you want to prefer the left option, which is based on the permutation tests. And there's also great work by Caroline Strobel from I think from Munich, and she with her colleagues they have a very nice paper showing these bias happening with simulated data.
Right. As usual, we also want to get a look at the our performance metrics of the model that we have created. So let's make some predictions, as we have done often before, and then build a confusion matrix out of that. So this is once again the in-sample performance, the data that it was trained on. That's where we are looking at the performance, and yeah, looking kind of okay. That great. Well, let's take a closer look at the validation of the performance on the validation data set. And yeah, the difference between in sample and out of sample. Sensitivity, just looking good. Doesn't look like this random forest has been overfitting. Well, that's good. The next thing is a causal random forest. Let's take a closer look at the code right here. And in this case, if we want to use a causal random forest, well, we need some variable to serve as the treatment that we want to investigate. And the data set that we have been using so far doesn't really have a treatment per se. We could generate some artificial data set, like in those plots we looked at in the slides. But since we're just trying to investigate how to use this method right here, let's just use our own variable, pick one of them and say that this is what happens if we say this is the treatment variable. And so in this case, we can use we're just using the verification status. If we look at the data set itself, the verification status, let's see, right here, is a categorical variable with either verified or source verified or not verified. So what we could do, or we can interpret this as, okay, let's say we are choosing randomly whether to verify the status of one of those entries in here or not. So this is reasonably close enough to something we can treat as a treatment variable. And the library that we are using right here, this method later, it wants or it prefers a numerical variable. It doesn't accept categorical like that. So what we're doing right here is converting this verification status feature depending on whether it is not verified at all or verified in either on the source or basically verified. We turn that into 0 or 1, both for the small data set and for our validation data set. Another restriction on that the causal forest library is putting to us, like we encountered before here, it really doesn't like the categorical variables. The earlier models did the work for us. They automatically, under the hood, transformed the different categorical variables into one-hot encoded dummies. Now we need to do it ourselves. So we've got a list of the variables that we do not want to take over because we've already dealt with this verification status ourselves. And the rest we can tell are to create a matrix version with dummies in it for us. So if we do this and we take a look at the result, what does it look like?
And it typically takes a little bit, yeah. But
I'm looking at that right here.
Oh, that's already done. Oh, that's very fast. But the point is, why do we need to split all of that? So the reason is that the algorithm afterwards wants to have every piece of data separate from one another, right? So it wants to have what is the target variable. So what is the y? And it wants to have also the treatment variable separately from the all the other covariates that we have that we're going to use to measure the heterogeneity. So that's why we need to have all those three separate from one another.
Now we have got one hot encoding of all categorical variables, and the rest is fine as is. So now the data is in a format that we can actually use. So we've got the data set without the features, or they're no longer features. They're now our treatment and our result effect. So this is the matrix of just our features and the result, the outcome, and our treatment right here. So we're feeding all of that into the causal forest model. Once again, we've got this mtry parameter that we've already seen in the regular random forest model. And we can tell them once again how many trees there should be. So let's train the model. And since I'm using the small data set, this is reasonably quick. And it's giving us some variable importance right here. Well, cannot see those numbers so well. Let's create another.
Seems quite small, right? And also one thing that should also keep in mind, perhaps.
And unfortunately, I think it's giving us just all of the different variables in a row. I mean, considering the one-hot encoded categorical variables, there are many features by now. So I'm not sure if there's any way to tell right from this plot what these important variables are.
It's a little bit less sophisticated than the plot that we get from the original random forest, but you can still use this if you use the other dimension.
But we can now get the conditional average treatment effect by taking we're predicting it on with this model and creating a new variable with the predicted treatment, and that way we've got the predicted treatment effect. So we've got.
And then again to stress that, so this is the predicted treatment effect, considering all these heterogeneous relationships that we find from the splits in the tree, right? So this is not in contrast to the original random forest. This is not the predicted Ys. So very, very important to stress that. So you're not getting any predictions on the Ys here with this predict object. So it's a predicted average treatment effect on the.
Right. Remember, we were using a binary variable for our treatment. So either it was not verified or it was verified. And between two very similar samples, presumably, if one of them was treated and the other one was not, what was the effect? And since this is achieved by using all of these different leaves in the tree, we can even get a number of observations in that leaf. And so this way we can get a histogram of the predicted treatment effect for all of the different samples in all of the different trees and all of the different leaves in our forest. And so this way we can estimate the causal effect of the verification on the outcome. Now, from this histogram, we can now then take average. So this is then the overall average treatment effect, both direct and indirect and across all samples put together. This tree gives us the power to give us a predicted treatment effect for any given sample, but ignoring all of that and averaging together, this is the result that we've got. And earlier we mentioned the no doctor situation. One of those this is one of those terms from the literature that is possibly confounding estimations of causal effects. For example, imagine when there is a new treatment in a medical situation where we want to estimate its effect. And we're doing this by assigning a doctor to decide which patients should get the treatment and which patients shouldn't get the treatment. And the thought experiment of the perfect doctor is, what if there's a perfect doctor that somehow intuitively assigns the treatment to all of those patients where it helps and keeps the treatment away from all of those patients where it would not help? Then if we are, this is basically a violation of the assumptions that we made earlier, because the consequence would be that the treatment effect would seem better than it actually is. Since in our treated sample, there are only patients where it actually helps, it seems better than if the treatment was distributed randomly. And that's why it's maybe a good idea to look at the average treatment effect only on treated observations. And what we can see right here is that they are reasonably close together. This, if I'm interpreting it correctly, is a good thing, because it should have created the tree in such a way that it is comparing treated observations and untreated observations that are similar enough that the treatment effect in the counterfactual world that we cannot observe should be the same.
So this is getting this into the framework of causal inference. So that's basically the ATT, the dear known ATT. So the average treatment effect on the treated, a la Evans and Unclus, where this is very, very thoroughly explained. And we have also a question here on the chat. So Sebastian is asking, do we interpret this as the average increase in the probability of default for those observations that were verified? Exactly. So in this context here that we have, so we interpret this effect as the effect of the treatment. So having the income verified, yes or no, on the probability of defaulting. Yes, so very, very good point.
It's actually interesting that this is a positive number. Intuitively, I would have thought that verification of some sort should hopefully reduce default, but this, after all, this was not true treatment. Perhaps all of those loans that received treatment were ones that actually were already considered kind of risky, and that's why they were subjected to additional treatment. So that's why we once again run into the problem with the assumptions of estimating causality that were not really well followed here. In this case, the treatment was not assigned randomly independently of the other covariates, but that's why, to answer your question, like Gabriela said, yes, that's exactly how we would interpret this 5% right here.
Yes, and chances are very high that those individuals who were asked to provide additional documentation on their source of income, because this was not randomly assigned, chances are these are exactly people who seemed riskier to the borrowers in the first place, right? So this is highly endogenous here and would explain why we would see a positive effect instead of a negative effect, which would be more intuitive, right?
But this also, once again, is a very good way to illustrate actually that even though we've got this model of a causal forest, which is doing it the best it can to take care of all of those different situations. It's grouping together similar situations. It's trying to increase heterogeneity. None of this helps if we are not following the basic assumptions we had originally. It doesn't get rid of the fact that perhaps a high default chance is causing verification rather than the other way around. It's still, there's no free lunch. Ideally, we would want a scientific double-blinded experiment with in a lab, but that's not what the data is giving us, and that's why we still need to take this causal estimate right here with a grain of salt. Right. Unless there are any other questions regarding this, so let's go on to gradient boosting. Once again, code with both big data set and the small data set. And not so much preparation right here. This is another one of those another one of those packages that can deal with all of the different issues in the data. And some of these new hyperparameters that we've mentioned are visible right here. This is the learning rate. Basically, the higher that this is, the more each additional tree in the sequence will take full advantage of any residuals that it can see and will fully try to get rid of it. In this case, we're setting it to a reasonably small number as is a good starting point. The trees themselves, they are really small. They don't need to be big. That's why we're boosting. And we're using some stochastic gradient boost right here, since not every tree gets the same samples. There's certain randomness in the way they are initialized. Then maximum number of leaves. The disadvantage of using so many different packages for illustration right here is that the same parameter always has different names. Once again, it's a good idea to look at the documentation for these packages to find out how to use them and what should be used here. And in this case, cross-validation is baked right into the code that the package is offering us.
And again, the same. Sorry, just one comment. Again, the same principle applies here. So the options that we're giving there are a fairly small fraction of all the things that we could play around with in the algorithm.
Yeah, the documentation would show us that, and even right here, just hovering with my mouse, it's giving me a small preview of the parameters, and even that one, I'm not sure if you can read it off the text that's too small, but even that one is truncated. So there are possibly many more parameters.
Oh, yeah. No.
As you can see here, it actually provided the results as they came in, kind of, and it was forced to run this sequentially, and so it's giving us all of these different iterations. Let's take a look at the model that was created. In this case, it's not showing us all of the different weights, and it's not showing us the confusion matrix, but it's giving us some other information about the model itself. There were 50 iterations and 32 predictors, so features. 6 of them had non-influence, so that's interesting. Let's take another closer look. And this gradient boosting, once again, gives us a list of all of the different variables, including their relative influence, both as a exact number and as a plot in this case. Many of these different features didn't play a role in predicting the gradient boost. Loan amount in this case was actually more influential rather than total payment. So this is interesting that it's giving us a slightly different result than the earlier models. But once again, this is something that you need to take care of on how to interpret. This is just how well this model was able to use it. Doesn't mean causal influence in any way.
But still looks like, let's say, the top 3 are the usual suspects that we got in the random forest and also in the single trees that we estimated yesterday. Right, so we see these seem to be at least good variables in predicting the probability of defaulting. Whether this is something causal or not, we cannot say, but seems to be good predictors of this variable.
Right. So we can also just tell it to ignore all of these useless variables and just show us the top 10 in terms of relative influence, or another metric that we can see right here. Basically, also just a different method of estimating this.
Which is, again, one that we would prefer because that's based on permutation tests and not based on the improvement in the node impurity that suffers from all the biases that splitting on the Gini index suffers from.
Yes, very good point. And we provided one parameter right here, the Bernoulli deviance, which is basically just a measure of the difference. And ideally, we would want this to be as small as possible so that the model converges, and at the end of the day, we are finally arriving at the true result. And what this plot is showing us is how this has been going over time, but once again for both in bag and out of bag across all of the iterations. And it looks like from this perspective, like a very linear result, as if we could have gone even further.
And that's something whenever you have those different iterations of the models, especially those models where you're building upon the original solutions, that's always a good idea to look at this graph of the performance against what number, how many trees did you estimate? Because sometimes you might even recognize the other way around. Like you see, okay, I reached a plateau already 300, 400 trees ago. So I'm kind of wasting time by estimating so many of them, whereas I could have reasonably similar results by cutting my training period short, right? So here looks like we would actually need a couple more trees, or at least they would help us to reach this level where nothing else is changing. But it could also be the other way around.
No, I was just really curious, and I wanted to see what would happen if we are letting it run for even longer. Hopefully this doesn't take too long. I just wanted to see. And there we go. So let's take a look at this. And when we're doubling it, it's starting to slow down. It's no longer just quite so linear. Anyway, another plot that is provided to us is now looking at one variable in particular, and sorted by all of the different loan amounts that are available in the data set. What is the prediction made by our model? So in this case, since the loan amount was one of the very first parameters, actually, apparently this looks like it was a single node, or it was no longer very much changed by the different no longer changed by the later trees. In this case, it looks very constant once the loan amount exceeds a certain point.
And that's a very good intuition that these values, they landed in the same node. Now that can be for two reasons. So that could be, it could really be that after some threshold, the loan amount does not have any additional correlation. I'm careful here not to talk about effect. Let's say the correlation does not increase with the propensity of defaulting. But another thing could be that we simply do not observe data after a certain threshold, right? And actually, I was just quickly here running, so describing the loan amount variable. So the 95th percentile is at 33,000. So everything after that is not observed in our data. So the model is just assuming that the effect, or at least the relationship, will be the same as for those that we have observed that go up to this threshold. So something that this implementation, this is a typical example of a partial dependence plot. So this implementation directly out of the box from GBM does not let you see where do you have the density in your data. So it's just taking loan amount from 0 to a very, very high value and saying, okay, let me plot the predictions according to the model whenever I change this variable and leave all the others at their means. But what we would actually want to see here is where do we actually have density in our data set? So do we have several values, for example, larger than 20,000? Because if not, then we want to be very, very careful to interpret the results in these regions where we do not have enough data.
As we can see just by a very quick investigation of that variable, 3/4 of the samples are below this point. So even though it looks like it's somewhere in the middle right here, the vast majority of data is on the left right here. And it only gets worse as we move further to the right. Beyond this point, only 10% of total samples is left in here, and the majority in there.
If I'm not mistaken, the PDP package, I think it's also goes by the same name. I think the PDP package does plot this density there. If not, the ICE package definitely does, and you can do the you can use the ICE package to say you just want to do PDP because it can do both. And the ICE package definitely shows the density of the data.
Yeah, but now I would need to import the libraries and so on, and
yeah, we don't have them in our code because we don't use them there. But I just put it here in the chat so that others can also explore it if they want.
Yes. We can also specify exactly the number of trees. If we're saying just a single tree, we can get a similar measure just as before, just for a single tree, and yeah, with all of the caveats that we mentioned already. As usual, we are interested in both the confusion matrix and performance measures on both the in-sample data and the out-of-sample data. And looks like sensitivity is gotten really, really bad, but specificity and so on the out-of-sample data, they got really well. Oh, it actually managed to hit every single one of these perfectly, but the model that I just created right here really, really struggles with these. That's interesting. Not sure what happened here.
That's using the loan string small, right? So probably had less opportunity to learn from those cases that are positive, because then we have even a smaller share of data, and these are already just represented for so 20% of the observations. So I guess that's probably what we have there. And by the way, the results in the slides are from XGBoost. So I think even I can check, I think I have it here stored. Even the results of GBM in the full training data set were not very exciting in comparison to the XGBoost ones.
Yeah, and particularly for a small data set, not doing so well. But that's what the remaining code right here is for, using this one big library that a lot of optimization has gone into. Once again, we need to put the data into acceptable format without missing values, and making explicit what we want to do with the I think categorical variables are fine in this case, but we need to make sure that we tell it how to deal with the default result here in this case that we want to optimize for this. So this is the code how to call the XGBoost model from R. Similar thing could exist in Python or whatever. We've got a regularization term to make sure it doesn't overfit too much. This is another shrinkage parameter, both also to avoid overfitting. Once again, the tree size. How exactly it should optimize this. It's a binary decision problem, and it's providing us ultimately a logistic regression in the form of a number between 0 and 1 at the end, early stopping criteria, parallelization, all of these different parameters that and more that are available to this. So let's build a model. And since this kind of library is probably expecting to run for a long time, it's giving us some information in between, but just on the small data set, it's running really, really quickly. And we can also ask it about variable importance as before. And it looks like total payment once again wins as the supposedly most important feature in all of the data, with the other ones close behind. The number of leaves, well, as more and more layers in the tree get added, I guess. Do you know how to interpret this plot, Gabriela?
So if I'm not mistaken, what it looks at is what happens with the depth of the model once we start adding more trees for one, and the other was how do I contribute to decreasing my error as I go deeper within each tree. But we can also go here just to check on that. And by the way, I just ran here the results on the full training data set with GBM. It did perform slightly better than what we had before. So we were roughly around 60% sensitivity instead of, I think, 19, right? That's what we had before. So let me go here, GG motiveness, because I think that's how we would see that. Oh yeah, right. So that's another way of seeing that. Yes. Exactly. So how do the weights? So we are plotting. We're seeing the number of trees, and we're seeing how adding more trees actually influences the weight of those leaves. And the weight, again, is a function of how well of a job am I doing there. So as I'm adding more levels to this tree, I'm making it deeper, then I have my leaves coming a little bit earlier, a little bit later, if I have more splits in there. So how do these leaves afterwards change the weights in the data that is coming to the next tree? And if these leaves are doing a good job, then more observations are going to have a lower weight. because now that they're well predicted, we do not need to focus on them anymore. So the weight is going to be less. And in that case, these leaves are changing the weights more dramatically. So that's what actually we're seeing there.
And ideally, what we would want is to have the training go on until these weights are close to reaching zero, because then presumably the model cannot get any more better performance out of it. However, caveat, as usual, if we actually do reach that point, we're at risk of overfitting because it just learned the data too much. And what we are seeing right here is also somewhat different. It doesn't reach zero, but rather it reaches a weight of 0.2 and kind of fluctuates around right here. The way I might interpret this is that the leaves are kind of overshooting as any new tree gets added right here. I think in this case, we probably do not have enough data right here just to make it capable of finding generalizable properties. So either we would want to decrease the learning rate so that these effects are getting a little bit smaller, but this is just the consequence of using the small data set. Let's run it on a large data set. Nah, I didn't have the data prepared. Oh, well.
It's a little below that there. A little bit below. A little bit more.
Oh, yeah.
There, yes. As it likes to have this matrix with dummies already. It doesn't want to do this job on the background for us.
Yeah, it's expecting to have all of the different preparations from before, but so far I've always run the code with the small data set, so that's why it's not getting everything it wants to. Oh well, it's not really that bad. And as usual, even for the small XG boost, we're both interested in the in-sample performance. Kind of what we're really interested in is the out-of-sample performance. And even on the small data set, this is looking better than most of the models saw previously.
Now you can see why XGBoost is very often the sweetheart of the data mining competitions. So you see, even with a very, very small data set and a handful of variables that seem to have good information to predict default, it seems to be doing a wonderful job, and especially on the validation data, right?
It's easy to get good performance on the training data, just learn everything by heart. Really care about the validation data. And ultimately, the test data at the end of the day. And the real data.
And perhaps one point there, how does XGBoost manage to get this trick done of doing this estimation process very fast? So you might remember we talked earlier about random forest being able, because the trees in random forest are independent from one another, right? So we don't build them sequentially. So this is something that you can actually parallelize. So you can say, I create all the different bootstrap samples and I parallelize the estimation of the trees. Now, on the other hand, with gradient boosting, this is in principle not possible, because the second tree builds upon the results of the first tree. And then the third tree builds upon the result of the second one. So this is something that in theory, you could not parallelize. Now, the developers of XGBoost came up with a very, very clever trick. So what they said is, okay, the tree building itself, true, this is something that I cannot parallelize. But within a tree, I can parallelize the estimation of the nodes that are in the same level. So maybe if I let me try to share here the board again. So we have the old board here. So if I say, okay, so within a tree, so I started growing this tree here. So I have my first split. And now after that, I can parallelize these two branches here. I can do this in parallel because what happens here has in principle nothing to do with what's happening here. So these are two independent roads, if you will, right? So I can parallelize that. And even if I go further, let's say I go here, now I have 4 different roads where things are happening. I can parallelize those 4 as well. So that's a very clever trick among a couple of other tweaks that the developers of XGBoost came up with that makes this implementation very, very fast.
Another big factor is XGBoost is compatible to run on your graphics card. So if you've got a big gaming PC or another expensive NVIDIA GPU in your machine, then XGBoost is capable of using that, and that sort of thing makes it way faster, way faster. Anyway, there's a question. Is it possible to obtain the split point value, maybe the mean for them, for the most important variables in a random forest algorithm or gradient boosting? The thing is, this is no longer just a single tree. So there's no longer just a single splitting value.
I mean, in theory, this is not something that is going to be ready, like plug and play. Like there's no function that would give that directly to you. But whenever you're estimating those models, you might know that they're always stored in an object. And this is typically a very, very large list. And within this list, you also get the splits that you have in the tree. So let's say if you say, okay, actually, I would like to see what is the average, with all the caveats that an average might mean in this situation, because you can have this variable appearing at several different places in the tree, and in each place having a different split point. But you could, for example, go and say, okay, let me extract the information from this object and see what is the average value that you got from the split on the variable X. Another option would be to use these interpretability methods. So for example, as you have seen in this PDP plot, in the regions where you had a certain value there, this is highly indicative of these observations, they landed in the same place, right? So this is also something that could give an indication of, well, there's definitely a split here on this variable around this value, and this is a terminal node there. But again, this is something that if you would like to have, it could derive from the object containing the final estimation of the random forest or of the gradient boosting.
Yes, definitely. Even no matter what the model, all of the weights are always available to you if you dig deep enough.
Can I say something quickly? It's just
Yes,
a reminder, we're going to share the poll of the day. So if you can please answer it. Vamos a lanzar en este momento la encuesta del día, por favor, por si lo pueden contestar. Thanks.
And as usual, the next day we'll start with another Q&A session. So feel free to think of more questions for tomorrow, play around with the code, run it, and see what happens.
Any other comment, question?
Let's see here. No, nothing on Q&A, nothing in the chat. Also on Slido, everything is clear. So then thanks everybody for your attention, and we'll see you tomorrow.
Thank you, Gabriela. Thank you, Sebastian. Very interesting. So we'll see you tomorrow early in the morning. Take care.
Take care. Bye-bye.
Bye.
Bye-bye.